Welcome back, everybody. In this video, we'll be starting Chapter 8. As always, we want to give a quick overview of what the chapter is about before we get into it. The chapter has 4 sections in it. The chapter is called Hypothesis Testing as part of what we're doing when we do inference. The first section is kind of introductory. As is usual, it says basics of hypothesis testing. In this section, it's more conceptual than a lot of the chapters we've done so far. So there's more definitions and ideas in this chapter, or in this section of the chapter. And then once we've gone through 8.1, which will take some time, we'll be ready to do 8.2, 3, and 4. So 8.1 describes what hypothesis testing is in general, and then 8.2, it says testing a claim about a proportion, 8.3, testing a claim about a mean, and then 8.4, testing a claim about standard deviation or variance. So in a way, this is going to kind of resemble Chapter 7, where we first learned what a confidence interval is, and then did it for proportion, and then we went over again for means, and then we went over confidence intervals again for standard deviation. And along the way, we picked up a couple of new tables, the t-table and the chi-squared table. So in this chapter, we'll be doing something similar. We're going to learn about hypothesis testing. Then we're going to apply that to proportions. Then in the next section, we'll apply it to means. And then in this section, at the end of the chapter, we'll be applying it to standard deviation and variance. Fortunately, we're not going to have any new tables, but we will have used of the z-table and chi-squared table that we learned about in the last chapter. So let's get started. So first of all, definition. In statistics, a hypothesis is a claim or statement about a property of a population. So you might be saying something like, okay, I think the mean is equal to 3, or the standard deviation is equal to 2.1, or the proportion of people who sleep with socks on is 0.84. So that's a claim or statement about a property of a population. A hypothesis test or test of significance is a procedure or process that we can follow to test the claim about the property of a population. So the first section is on basics, and one of the most important things we need to know about is the rare event rule for inferential statistics. And to introduce that, let's consider tossing a coin 20 times. I told you at the beginning of the semester that we can assume that in this class, coins are fair and dice are fair. Boys and girl babies are equally likely. But let's just say we've got some coin, and we don't know if it's fair or not. Maybe it's a loaded coin. It's more likely to come up tails. We don't know. Most coins, they come up heads or tails with a probability of 1/2. So let's say we toss this coin 20 times. In part A, the coin, let's say it comes up tails 12 times out of 20. The probability of getting tails 12 or more times is about 0.251. That is, if you were to toss the coin 20 times, about a quarter of the time you do the 20 toss process, you would get tails 12 or more times. That's not that weird. So that is not enough evidence to conclude that the coin is not fair. Okay, the coin comes up tails 5 times. Let's say the coin comes up tails only 5 times. If the coin came up tails 5 times, the chance of that happening with a fair coin is about 0.02. Okay, the chance of that happening is low enough to suggest that the coin isn't fair. Okay, so basically we have some sort of an assumption, in this case that the coin was fair, and if we have some evidence that is contrary to that, and the probability of us getting that evidence and the assumption being true, if that probability is low, then we conclude, well, we can't argue with the data, so what must be false is the assumption, okay? And that's the rare event rule for inferential statistics. It reads, if under a given assumption, the probability of a particular observed event is extremely small, we conclude that the assumption is probably not correct. Again, you can't argue with the data. So if you've got some assumption and then you collect some data, and that data, the chance of getting that data is really small under the given assumption, then something's got to give, and what's going to give is that assumption. So when you're creating a hypothesis test, you need to do something called setting up a hypothesis, because you're going to test it, right? There's actually two hypotheses. There's a null hypothesis and an alternative hypothesis. Null means kind of like zero or empty or true by default in this case. The null hypothesis is it's going to be a statement about P, the proportion, mu, or sigma being equal to some value. The null hypothesis is always assumed to be true. We're going to go through a process that we, of course, haven't talked about yet, where we decide to either reject that null hypothesis or fail to reject it. How we would write the null hypothesis is we write H0, 0 is like null, H0, a colon, and then a statement about one of the parameters, like the examples you see here are P equal to 0.3, mu equal to 1.7, and so forth. There's an alternative hypothesis. Our book calls this H1. Some books may call it HA, but it's H1 in our book, so that's what we'll use. It's a statement about the parameter value that has to differ from H0. If H0, the null hypothesis, is not true, then we need to think about what is true, and that's going to be the alternative hypothesis. In this chapter, this is going to involve less than, greater than, or not equal to. So some examples might be that the proportion is not equal to 0.3, the mu is greater than 1.7, or the sigma is less than 0.42. As a side note, some books allow the H0 to include the equal to case. Our book doesn't do this, but in any case, the H0 and H1 are always mutually exclusive. That is, if you know H0 is false, then H1 has to be true. And if H1 is false, then H0 has to be true. Okay, so also the H0 and H1 can't overlap. For example, we can see at the bottom here, P is less than or equal to 0.5, P is greater than or equal to 0.5 is our alternative. What if P is equal to 0.5? Well, that would fit into both cases, and we will not have that happen ever. All right, throughout, the null hypothesis is going to be the one that is assumed to be true. In our book, the H0 and H1 are always chosen so that equality is included in H0. The evidence obtained from our sample may be used to reject H0. If the evidence is not strong enough, then H0 will fail to be rejected. It will never show the null hypothesis is true. So it's important to remember that the null hypothesis is always assumed to be true, and the outcome of the procedure that we follow is, there are two possible outcomes. Either that our evidence is strong enough to make us believe that the alternative, H1, is true, and reject H0 in favor of H1. On the other hand, if our evidence is not strong enough, then that does not prove that H0 is true, but it just fails to prove that H1 is true. And there's a subtle distinction there that takes some thinking about to get used to. An analogy that can help with this is to think about the way that our trial by jury system works here. In the US, people are assumed innocent, right? So Joe is innocent. Okay, people are presumed innocent. And even if they're arrested, they're still presumed innocent. They go to trial, and then that whole process happens. People present evidence and arguments and so forth. And then a decision is made. Let's say that it's by a jury. So either Joe is innocent or Joe is not innocent. Joe is guilty. The assumption is that Joe is innocent, right? So what can happen as a result of the trial? Well, if there's sufficient evidence, okay, Joe was seen walking out of the jewelry store with a bag full of jewelry, and the clerk says, okay, yeah, that was the guy. Okay, well, then, yeah, Joe is the guy. So, okay, Joe's guilty. So if there's sufficient evidence, we say, okay, we can reject our assumption that Joe is innocent, and therefore we have to conclude that Joe is guilty. That's one possibility, if the evidence is strong enough. If there's not sufficient evidence, okay, let's say nobody saw Joe leave, he had a mask on, something. Okay, so there's not enough evidence. Okay, if there's not enough evidence to say, okay, Joe did it, that doesn't mean that he didn't do it. It just means that we aren't able to prove that he did. Okay, so that's basically the way that the process is going to go here. We'll always set up our null hypothesis so that that's what we're assuming to be true. And then the alternative, either we don't know if it's true or not, the sample data may cause us to reject the null hypothesis in favor of the alternative, but the sample data will never show that the null hypothesis is true. All right, so there's kind of a long flow chart in our book that covers how to do this. So this is really kind of lengthy. What we're going to do here is I'm going to kind of go through the flow chart at kind of a higher level view for each of these boxes, and then we'll take each one separately kind of in turn and go through it more specifically. So the steps to follow to do a hypothesis test are to, this is box one, identify the claim to be tested and express it in symbolic form. So if you want to know, okay, well, the proportion of people who sleep with their socks on is 43%. Okay, then we'd write P equals 0.43. Okay, identify the claim and write it in symbolic form. Okay, so let's use as an example. Let's say the urgent care by your house. Let's say you've been there a few times. You feel like the wait time is long. So I think, okay, the average wait time at the urgent care is 40 minutes. That's going to be our claim. Writing it in symbolic form, we'll say, okay, the average, that's mean. So mu is equal to 40. That will be in minutes. Then 2, give the symbolic form that must be true when the original claim is false. So if it's false that the mean is 40, that's what has to be true. Well, we could say it's not equal to 40, or greater than 40, or less than 40. Okay, those are the 3 ways that the mean can fail to be 40. Given what you suspect to be true, okay, well, it's unlikely that the mean is less than 40, and saying that it's just not equal to 40 is not that specific. Okay, if nobody's really going to care if the mean is not exactly 40 minutes. Most people are going to want to know, okay, is the mean more or less? Okay, so we're going to go with greater because in a way that's worse. Okay, you don't want to wait a long time at the urgent care, right? So 3, identify the null and alternative hypothesis. Consider the 2 symbolic expressions so far. The alternative hypothesis H1 is the one not containing equality. So H1 uses the symbol greater, less, or not equal to. The null hypothesis is the one where the parameter equals the fixed value being considered. So that's what you see here to the left, the results of step 3. Okay. Step 4, we're to select the significance level. With the significance level, that's called alpha, it's based on the seriousness of what's called a type 1 error. What a type 1 error is, we'll talk about later. Basically, you want to make alpha small if the consequences of rejecting a true null hypothesis are severe. More on that later too. The values of 0.05 and 0.01 are commonly used for alpha. By the way, the alpha that you see here is really closely related to the alpha that we were using in chapter 7 in conjunction with confidence intervals. Okay, basically, the part about type 1 error and rejecting a true null hypothesis, that part we'll deal with later, but you want to pretty much think about the alpha will be smaller if it's something where there's a lot at stake, basically, in getting it wrong. If you're testing like the effectiveness of a medicine that you're giving to babies, okay, then that's serious, okay? That's one thing. If I would use an alpha that is small, like 0.01 for that. If you're testing whether people prefer chocolate chip cookies or Oreo cookies, okay, to me that's not that big of a deal. And so we could use a lower alpha like 0.05 or even 0.1 for that, okay? That's deciding on the alpha is something that you develop with experience. Usually though, it's 0.05 or 0.01. Okay, identify the test statistic that is appropriate to the test and determine its sampling distribution. That is it a normal distribution, a t-distribution, or chi-square distribution. So going back up to our hypotheses, for 5, you're going to need to identify the test statistic. Here, and the one that I'm doing about the urgent care, it's about the mean. So we'll either be using Z or T, right? If our null and alternative hypothesis were maybe something about the variance, or let's use standard deviation. Let's say the standard deviation is 5.1, and our alternative is that the standard deviation is less than 5.1. Okay, then we would be using the chi-squared table, and we would be using chi-squared as our test statistic. So that's 5. We're going to identify the test statistic. Once you've done that, notice that this branches. There's 2 paths you can take. There's basically 2 ways that you can finish the hypothesis test. There's something called a p-value method, and then there's something called the critical value method. It's also called the classical method. So we'll take the one on the left first. That's the p-value method. So by the way, you'll notice in here that it is a capital P, and that is more having to do with probability, and we'll get to what that is when we get more specific. But for now, know that it's not P for proportion, okay? It's P for probability right here. So what we'll do is we'll find the value of the test statistic and the p-value. That'll be a probability value. We'll draw a picture of the distribution and show the test statistic along with the p-value. We're going to end up rejecting H0 if the p-value is smaller than our significance level alpha. We'll end up failing to reject H0 if the p-value is bigger than alpha. Moving over to the right side, the classical method, you find the value of the test statistic and the critical values. Draw a picture of the distribution showing the test statistic, critical values, and the critical region. Box 7, we'll make a decision. We'll reject H0 if the test statistic is in the critical region. We'll fail to reject H0 if the test statistic is not in the critical region. This part may not make a whole lot of sense right now, boxes 6 and 7 in these 2 different methods. You really have to actually see how this is done in order to really get it. But for now, know that there's 2 ways of actually doing the test. One involves probabilities and is called a p-value method. One involves critical values and is called a critical value method. And we'll go over the specifics of how you do these a couple of slides from now. Okay, then you'll finish, either way, whichever method you choose, either way you'll finish by restating the definition in non-technical terms, okay? So you restate the previous decision in non-technical terms and address the original claim. So let's say that for our urgent care problem, we ended up deciding that, okay, there's sufficient evidence to reject H0 in favor of H1. So we wouldn't want to just say, okay, let's reject H0 and leave it at that, okay? Because people who don't know statistics, that's not going to mean anything to them, right? If you go and tell someone you live with, okay, I rejected H0, they're going to say, okay, well, yeah, so what are you talking about? But if you say, okay, well, there was sufficient evidence to believe that or the mean wait time at the urgent care is more than 40 minutes, then okay, then that's something that is more easy for us to relate to, and that's what box 8 is about, where you want to rewrite your statement in plain English, not in terms of statistics, H0s and H1s and stuff. Okay. So I realize there's a lot to that flow chart, but it will get better as we get more into details. Okay, a note about making up your own claims or hypotheses. If you're going to conduct a study or experiment and you're trying to use a hypothesis test to support your claim, you want to rig it so that the claim is worded so that it becomes the alternative hypothesis. Remember that we're assuming H0 is true, and the experimental data may or may not show that H1 is true. If your claim is H0, you have no hope of proving it. The only way you have a hope of proving your claim is that if it's H1. So state your claim so that it ends up being the alternative hypothesis. You can never support a claim that some parameter is equal to a specific value. Okay. All right, so now we're going to work into some of the specific details out of the long flowchart here. We have in this slide more to say about the significance level alpha. The significance level alpha is the probability of making the mistake of rejecting H0 when it's true. The significance level alpha is a specific criterion we can use to distinguish sample results that can easily occur by chance from those that are unlikely to occur by chance. So that right there is kind of awkward sounding. So let's see if we can think about an example. So let's say that we want to know the proportion of students at COD that work more than 20 hours a week, okay? And so let's say that we think that it's more than 40%. So let's say that we think that more than 40% work more than 20 hours a week. Okay, out of all the COD students, some of you work more than 20 hours a week, some don't. Does half the COD students work more or not? Okay, so the claim, what we're trying to show is that it's more than 40, okay? And it's about a proportion, so we're gonna say it's bigger than 0.40. So the default or null hypothesis is that it's equal to 0.40. It may in fact be less, but that will be included in the not H1 case, as it turns out. All right, so back to significance levels. So what's this about? So let's say that we're wondering if this is true about whether, you know, the proportion of COD students who work more than 20 hours a week, is it actually more than 40% or not? Okay, so we go out and get a sample. And maybe we've decided that, okay, well, based on our sample, we think this is true. Okay, we've gone through that procedure about the critical value or p-value or whatever when the time comes. We've decided that H1 is true. Okay, and so what alpha is the probability that we messed up. Okay, let's say that, well, H0 is a null hypothesis. Our experimental data may or may not show that H1 is true. Our experimental data, I've decided, has shown that H1 is true. Okay, it could be that the particular sample we got was compelling enough to show that H1 is true, but it may not actually be true, right? There's sampling variability in there, sampling error, so it may actually not be true. Okay, what alpha is the probability of making that mistake when H0 actually is true, right? So restating that more close to our example, we think, or my hypothesis here, is that the proportion of COD students who work more than 20 hours a week is more than 40%, okay? That may or may not be true. Let's say that I've gone out and gotten a sample and gone through all the calculations and I've decided, okay, well, I think it is more than 40%. The alpha is the probability that I'm wrong, okay? Because due to sampling variability, we might get a sample that supports what our claim is, and we might get a sample that does not. So if we set our alpha to be low, like 0.05 or 0.01, then that means our probability of mistakenly rejecting H0 is low. Okay, and that is kind of a restatement of what is taken here. Okay, so as an example, let's say a package label includes a claim that the mean weight of M&Ms is 0.8535 grams. And another package label includes the claim that the mean amount of aspirin in Bayer tablets is 325 milligrams. Which one has more serious implications? Rejection of the M&M claim or rejection of the aspirin claim? Is it wise to use the same significance level for hypothesis tests of both claims? So thinking about it, which is worse if it's wrong, okay? If the M&Ms don't actually have a mean weight of 0.8535 grams, then okay, then that's maybe bad for the company that makes M&Ms. But if there's slightly more, slightly less chocolate in there, that's not going to be a problem for your health, right? So the M&Ms thing is not a big deal. The aspirin thing is more of a big deal. So rejection of the aspirin claim is more serious. So you would want to use not the same significance level for both. So you would want to use a lower alpha for the aspirin one. All right, so we haven't finished up this section, but I wanted to make the video shorter. So we'll stop this video here, and in our next video, we will continue working on section 8.1.